right, welcome. So far just for the delay, but everything looks to be working. It's my pleasure to introduce Rich Franzin as this week's Colloquium speaker. I had to do the math. I've known Rich for 24 years now. Rich got his bachelor's degree from University of Wisconsin in Madison and did his PhD work at University of Illinois, Urbana-Champaign. But he spent most of his time as a grad student at the Harvard-Smithsonian Center for Astrophysics, where he worked with me as a part of John Cole's instrument group that developed the ultraviolet coronagraph spectrometer on SOHO. Rich worked on both data analysis and instrument calibration there for his PhD. And then after that, in 2002, he got a postdoc at Illinois, and then a research scientist position at the University of Michigan. And he's been working on a lot of other interesting things. He's applied a lot of sophisticated mathematical tomography analysis to solar physics, probably introduced many algorithms that solar physicists didn't know about until he found them. Rich actually practically invented the field of differential emission measure tomography, which has been a useful way of looking at data from the SDO satellite. And recently he's been getting into this high contrast imaging work for exoplanets, which he will talk about today. So welcome.
Online want to ask questions, they can do it in the chat.
Okay. So I'd like to thank Steve and the other faculty for welcoming me here today. It's an honor to be here, and so I hope I can show you just how interesting some of the optical problems involved in direct imaging of exoplanets are, and I'll just get started. So the outline of my talk is I'm going to talk about methods that have been successful so far in finding exoplanets. And I'm going to talk about the science drivers for direct imaging of exoplanets. And then I'm going to go over some of the direct imaging efforts that are underway or planned. Okay, so I'm going to talk about methods that have been used to find exoplanets, and I'm going to talk about the science drivers for direct imaging of exoplanets. I'm going to briefly summarize current and planned efforts, and this will bring us into the problem of speckles, and we'll hear a lot about them later, but speckles are the real problem when it comes to direct imaging of exoplanets. And that will bring us into current methods that are used to get rid of speckles and the problems associated with them. And that set of issues will bring us to my work in dealing with the speckles. And that involves a lot of regression modeling that I'll talk about. So this chart here shows this chart here shows the number of exoplanets that have confirmed detections year by year, and the colors on the colors indicate the method. It's a pretty weak pointer. The colors indicate the method that was used to find them. So red is the radial velocity method, and we can see that up until about a decade ago, most of the planets that were found with the radial velocity method. Now, starting about 10 years ago, then the transits, the green, started becoming a more productive method for finding the exoplanets. And then the topic that I'm going to talk about, which is direct imaging, is given by that little tiny sliver of blue. And so it really hasn't produced very many detections so far. But nonetheless, there are a lot of efforts invested in making this work. So just to show you what's going on with the transit method, this is a graphic from NASA. Basically, the planet passes in front of the star and creates a mini eclipse. And down below, you see the photometric signal associated with the mini eclipse for the planets. And then the radial velocity method, the basic idea is that the planet pulls on the star as it goes around it. And so to give you a little perspective, the redshift that Jupiter imparts to the sun is only about 13 meters per second. And that is a very difficult measurement in high resolution spectroscopy. It's possible, but not easy. And then looking at Saturn, that's only 3 meters per second. And that is really pushing things very hard. And then Earth is a measly 0.1. And people talk about doing it, but I don't think that we're close yet. So with transits and the spectroscopic method, they're indirect, meaning that they rely on how the planet affects the light from the star. And so with the radial velocities, you can get orbital parameters and planet masses, and the transits can give you the orbital periods and planet radii, but they don't allow us to see what's going on with the planet itself. So you can't really see what's happening with the planet's atmosphere. And also these methods are pretty heavily biased towards large planets that are close to the host stars. So you're getting a very biased sample of the planetary populations. So when we want to do direct imaging, it's because it's going to be the only way to see certain things like giant planets that are larger than 50 AU away. And so we need to fill in part of our sort of planetary population survey. And then, as I kind of hinted at before, if we want to see the atmospheres and key molecules that might be in the planetary atmosphere, such as carbon dioxide and molecular oxygen, we need to somehow see the light that is reflected by the planet. And in addition, there's a really great science case for seeing structures such as protoplanetary disks in young star systems that are in the process of forming. And I think a nice illustration of the need for imaging capabilities and imaging disks comes from the Alma Array. Now, what we see here is a picture of the Alma Array. That's the Atacama Large Millimeter Array, and it observes roughly from 0.1 millimeters up to almost 4 millimeters. And it's a pretty expansive array. It has 66 antennas with diameters up to 12 meters. And the largest baseline that they have set up at this point is 16 kilometers. Now, one really nice sort of handy thing to know is that if you calculate the lambda over d, angular resolution of Alma, you take 16 kilometers and divide it by 1 millimeter, that gives you 1/100th of an arc second. Now, if you take a 10-meter telescope and you're observing in the optical at 500 nanometers, that gives you the same number, 1/100th of an arc second. So what that means is that the optical telescopes and the Alma can see the same patch of sky at the same angular resolution. So you basically see two different components of the material at the same place. So so here's a beautiful image from Alma taken in the line of hydrogen cyanide. And so what I'd like you to point out is that there's a lot of structure to this disk, and it would be nice to take an optical measurement and see what this structure is. So now here's a cartoon, and basically the idea here is that with optical infrared, what you're seeing is the starlight reflected by micron-sized dust grains. And that comes from sort of the surface of the disk. So if you have a face-on protoplanetary disk, you'll be seeing sort of the micron-sized dust grains close into the star in the optical and IR. Whereas in the millimeter, you'll see stuff that's more in the middle of the disk and out to much larger distances. But what you see in the millimeter is you see continuum radiation from millimeter-sized dust grains, more or less thermal, but you'll also see emission lines from molecules like the hydrogen cyanide we just saw. So the optical and millimeter emission are a very complementary set of observations to help us try to understand what's happening in these planetary system formation processes. So here's just a few more pictures from ALMA, and there's a lot of structure in these disks, and seeing, so sometimes the gaps in the disk are cleared out by planets, and I don't have time to get into that, but the structure of these things is very important. Okay, so what are some direct imaging efforts? Well, the most exciting, soonest one is the James Webb Space Telescope, which will make infrared observations, and it will have a chronograph for observing exoplanets. And hopefully that'll be launched in the next month or so here, if all goes well. Also slated for launch in half a dozen years or so is the Roman telescope, and that will also have a chronograph, and that will be somewhat shorter wavelengths than the James Webb. And the Roman telescope is named after Nancy Grace Roman. Now, I had no idea who she was until they named the telescope after her, and then I looked her up, and she really had a brilliant career. So I just want to take a few seconds to talk about some of her seminal contributions. So she played a very important role for classification of stars and their motion. She was the first female executive at NASA. She was the first NASA chief of astronomy. She created the NASA Space Astronomy Program. And she was also very important in planning the Hubble telescope, and some people dubbed her the mother of Hubble. So space-based direct imaging efforts that are under study are HABEX and LUVOIR. NASA's studying those. And then there's another idea here called the star shade. And the idea is that you separate a blocker. So you have two spacecraft, and one of them is a blocker. It blocks out the sunlight, and you put the spacecraft holding the camera in the shadow, and then you look around the star shade to see the material around it. And all these fancy blades, they have that shape in order to control diffraction effects. But there are also ground-based direct imaging missions that are underway right now. What we see in the back is the VLT on Cerro Paranal, and that is, I think that's the host of that's the Sphere, the VLT Sphere project. But I mostly work with the last two, SCEXAO and MegaOx. I collaborate more closely with them. So, but wait, there's more. We're at the beginning of the era of the extremely large telescopes. They'll have diameters from 20 to 40 meters, and they all have plans for direct imaging initiatives. Now, so this is the European ELT, it will have thousands of mirror segments with a total diameter coming up to nearly 40 meters. This is the giant Magellan with 7 segments coming up to almost 25 meters when you put them together. And this is the 30-meter telescope weighing in at 30 meters. So the problem that you're confronted with when you try to see a planet next to a star is that the star is way, way brighter than the planet. So you're lucky if your planet is big enough so that it's only it's only one that the starlight is only 1,000 times brighter. And if you want to see a small rocky planet, you might be down to 1/1 millionth as bright, or 1/1 billionth as bright, or 1/100 billionth as bright. And getting to those extreme contrast levels would certainly have to be done from space. But anyway, so if you want to see a faint thing next to a bright thing, we can go back to old Bernard Lyot's idea of a chronograph, which he used to observe the sun. And what we see here are one of Bernard's first pictures with his solar chronograph. So we see that there's something's blocking out the disk of the sun, and you can see all of the solar corona material streaming off. So how does this Leo chronograph work? Well, here on the far left, what we see is the beam from the telescope filling the entrance pupil of the chronograph. The spot in the middle represents the secondary mirror, so that blocks part of the beam. But anyway, so the beam comes in and it hits a first focusing element, and in the focal plane, you put a blocker or some kind of focal plane mask. So up here on the top left, you see the spot on the blocker, and then down below it, you see what happens after the blocker. So you see a little bit of light diffracting around it. So now the light diverges from the focal plane, and then it hits another focusing element, which recollimates it. And then what we see in the next plane here is what's called the Leo stop. And that was one of Bernard's great contributions was he saw that when the light before it hits the Leo stop has this bright ring around the edge due to diffraction. Now the Leo stop just chops that off. So what you're left with is this part down here. And then you just bring the light to a final focus, and you've killed about 99% of the starlight. So that sounds good. Well, real optical systems have a lot more surfaces, and there's a lot more going on. So this is from the SCEX-AO test bench, where they try to achieve high contrast in the lab. And so the light is launched by a laser here on the left of the diagram, or the beam from the facility, from the telescope, can come in. And then it bounces all the way around. And I don't want to follow the light path, but the point is, I want you to see that this light hits a lot of surfaces and goes through a lot of optics before it finally ends up in the science camera down here in the lower left. So the only takeaway there is that it's complicated and there are a lot of optical surfaces. So now on the SCEX-AO test bench, if you just take a picture of that laser source, all you see are all these speckles, and these are vastly brighter in contrast units than any planet you might want to see. And so lots and lots of speckles. Now, you can use a deformable mirror, which I'll talk about in a second, to create a region of destructive interference, which we creatively enough call a dark hole. And so how does a deformable mirror do it? Well, you all understand what destructive interference is, but you might not be sure what a deformable mirror is. This is from the Alpo Corporation, and they make one of these. And so what we see here on the right is the surface of a deformable mirror, and the thing on top is a reflective surface, and the color is just telling you how high it is at a given point. But under it, what we have are actuators, and those actuators are what control the height of the deformable mirror. And then having a controllable surface like that allows you to create the region of destructive interference we saw here. So now, of course, on the ground, you not only have the hardware aberrations, but you have the atmosphere to worry about also. And the plan to deal with the atmosphere centers around adaptive optics, or AO. And just to understand what adaptive optics does is, if you don't have adaptive optics, you take a picture of this galaxy, it looks like this picture on the left. But then when you turn on the adaptive optics system, let me just say that this is blurred because of the atmospheric turbulence. So you have the atmospheric turbulence blurring the image in a different way every millisecond. And then when you do a time average exposure of like a minute or something, you just see all this blur. Now, when you turn on the adaptive optics system and do that same observation, you see a far sharper picture. And that's because the deformable mirror is compensating for the atmospheric turbulence well enough that you're largely recovering the lambda over d angular resolution of the telescope, as opposed to being limited by the seeing. So a little bit more into how adaptive optics works. So before the light, so in the diagram here, before the light gets into the telescope, it's been distorted by the atmosphere, and the atmosphere is just creating different time delays for a given wavefront. And so that's represented here. And then the light goes through the telescope's reducing optics, and then you get a beam that's maybe a centimeter in diameter. And then it comes to the adaptive optics system. So the first thing that happens there is the light hits this deformable mirror, and then the light from the deformable mirror bounces off of the beam splitter and goes to what's called a wavefront sensor. The wavefront sensor's job is to measure this distortion. It's basically figuring out what is the time delay at every point on the surface of the wavefront. And so the wavefront sensor measurements are processed by a control system. So you got to do some computations given, whatever measurements the wavefront sensor makes. And then the control system makes the command to the deformable mirror. And this is called a closed loop control system because what you're sensing is the corrected signal. Now, this update needs to happen at a kilohertz frequency because that's how fast the atmospheric turbulence evolves. But there's going to be a frame delay because you have to collect the photons in the wavefront sensor, and then you have to do some computation, and that takes about 2 milliseconds. So even though the update is every millisecond, you have a frame delay of 2 milliseconds, so you're always correcting old turbulence. And so what that means is you're never going to get a perfect correction due to this delay. Okay, and then, all right, so we're running, so the light that doesn't go through that doesn't get used by the adaptive optics system gets sent down to whatever imaging system you might be running. And in this case, we're talking about some coronagraph system. Okay, so let me just show you an adaptive optics movie. And so in the upper left here, what we have is a turbulent wavefront that hasn't been corrected. This is just what comes down from the sky. And then if you just were to bring that light to a focus, you'd see all these speckles, and you see the speckles and the turbulence both evolve at that millisecond time scale. Now, when you run an adaptive optics system, the wavefront sensor makes a measurement of this turbulent wavefront, and then it doesn't see all the high spatial frequencies. So what it finds is sort of a smooth version, a low spatial frequency version of it. And then when you subtract the fitted, so the deformable mirror implements this correction. And then when you subtract this top center one from the top left one, you end up with the top right one. And that is called the AO residual. In other words, it's partially corrected for the turbulence, but a lot of the high spatial frequencies are there. But you see in the center a very good kind of center of the airy spot. So the middle of the middle of the star's image looks pretty good, but then you just have all this high spatial and temporal frequency garbage going on around it, and those are, and that's an example of speckle. Okay, so now the first coronagraphs that were mounted behind adaptive optic systems saw images like this one. And this is a long exposure image. It's, let's say, an exposure time of a few minutes. And what you see here are speckles and no planets, and all these speckles are way brighter than any planet. So now these speckles, the atmospheric speckles, the millisecond ones that we just saw a moment ago, they kind of average out in a 1 or 2 minute exposure. They kind of lead to a smooth background. So these speckles are actually the hardware speckles. And they actually change on time scales of, a few minutes or longer is what has been found. And what happens is that the telescope hardware is under varying thermal conditions, and also depending on how it's mounted, there could be time varying gravitational stresses. So you have time dependent stress, mechanical stresses on the optics, and they make these speckles change at various time scales ranging from minutes to months. And they are the big problem in exoplanet imaging. It's very hard to deal with them. So the community has has developed a set of techniques that are pretty much all based on differential imaging, which I'll explain in a second. But the idea, and the most important of these, is called angular differential imaging, which I'll explain in a second. But the takeaway is that using these differential imaging methods, you try to find an image that you can subtract from this image that takes away all the speckles, but leaves all the planetary emission. So if you had the perfect background image to subtract, you'd be done. Now, this is how angular differential imaging works. So this is the south celestial pole, and so the stars rise in the east over here, and what you're watching in these black boxes is a little field of stars that are rising and setting as the observing night goes on. So again, here, this plus is the south celestial pole. Because the Earth is rotating, the whole night sky rotates around the south celestial pole, and the stars rise and set on these circular arcs. Now, but as these stars rise and set, you see that this little field of stars is rotating. So the image that you are hoping to measure is rotating as the night goes on. And you can set up your telescope so that it's always pointed at the star field, but it's not rotating. So in other words, the picture, so if you set up your telescope so that the telescope doesn't rotate and only points tracking on the circle, on the diurnal circle, what happens is if you take a photo of an astronomical scene at the various times in the night, you'll see the field rotation in the photos you take. Now, if the telescope isn't rotating, that means that the hardware system and all those optical surfaces aren't rotating either. And so that also means that the speckles that they are creating are not rotating. So the stuff that you want is rotating in this nice way, and the stuff that you don't want, which are the speckles, are not rotating. And angular differential imaging leverages this fact to get rid of speckles. So the problem with angular differential imaging is self-subtraction, because so here's an example, is when you try to find a good image to subtract, you would often end up subtracting off part of the stuff you want. And so this is a paper on ADI, an early paper, and you can see shadows ahead and behind the putative planet that result from the ADI processing. And what's happening is that these speckles are evolving over the course of the night. And so that when you just use the ADI, you're not really subtracting the right thing. So the poster child for problematic differential imaging is the star LKCA 15, and it's a T-Tauri system, and it's got a disk with 55 Jupiter masses in it, somebody thinks. And so what we see in the upper left here, there are different kinds of differential imaging, but anyway, in the upper left, we have an example, and they used ADI to claim a detection of a planet in H alpha, and you can see the planet they claimed here. And this Nature article went through a lot of analysis, and they made pretty convincing argument that they had detected a planet with ADI. And at one point, there were papers claiming up to 3 planets had been detected. Now, a later study with a different instrument, also using ADI, claimed to not see these planets. And so in this paper, they said that the reason that the Nature article, the planets they thought were being confounded by an inner disk. And so their idea was that the inner disk was somehow giving them a signal that through the ADI processing was, oh, come on. Oh. Sorry. Okay, so their idea was that the structure of this inner disk was getting confounded with planets. So here's a movie that illustrates things pretty well. So what we see here at the bottom is a planet traversing, and these are all ADI processed images. And so this planet is far enough from the star that it's detected fairly unambiguously. But if you had a planet that wasn't as bright and that was closer to the star, come on. All right. Well, so anyway, if you had a planet that was closer to the star, you'd see that it'd be very confounded by the speckles you saw. All right. So then what can we do? The planets look like speckles and the speckles look like planets. But if we look closely, the planets and speckles behave differently. So in my 2013 AppJ, I provided this plot. I simulated what a chronograph would see behind an adaptive optic system. And so I showed semi-analytically that if you look at notice the x-axis here, this is the time in milliseconds. So I showed analytically that if you were to look at what's happening in the image at millisecond timescales, the planetary brightness wouldn't change very much in time, but the stellar brightness at the planet's pixel would change a lot. It's much more volatile. So I normalize both of these curves to have a mean of 1 in the graph so you could see them both. But again, the planet light isn't changing very much on this millisecond time scale, but the starlight at that planet pixel is. And so let me get into what's happening here. So what we see here is, these are from the same simulations in my paper. And what we see here is an adapt. So there's adaptive optics, but there's no coronagraph here. And I haven't turned on the turbulence, but what we're just bringing the light to a focus. And so what you see is a perfect Airy pattern from the star because I haven't turned on the turbulence. But once I turn it on, you can see the center of the star's image is actually held pretty constant by the adaptive optic system. So at the center, it's not changing very much, but then around it, there's all this very volatile speckle. And so now I put in the coronagraph and I put a planet in there too at a 1% contrast. And what you see is actually a very similar thing. The planet is at the center of the planet's pixel. It's not changing very much in time, but all the stellar speckles are changing wildly at this millisecond time scale. So now, with all this millisecond data, you might wonder, well, what's the cost to all these rapid readouts? Now, there's a new generation of detectors that that have very little noise penalty or no noise penalty for rapid readouts. There's the electron avalanche photodiodes, the EAPD, and they have very little readout noise. And then there is the MKID, microkinetic inductance detector. And what we see here is an MKID in the background. That is a 35 by 35 array of MKIDs. And they can read out at megahertz rates with literally zero readout noise. So then, okay, so we've collected all this low noise millisecond data. So then what should we do with it? And then in my 2013 article, I said, well, let's try to give it to a regression model that estimates the aberration that causes the speckles and also estimates the image of the circumstellar material at the same time. So the assumptions in the regression model are that, well, I have a couple different regression models. So one regression model, I assume that you know the statistics of the AO residual wavefronts. Remember, the AO residual is the uncorrected part of the turbulence. So I assume you know those statistics, and I leverage that to create one of the estimators called the bias corrected estimator. But if you don't know what those are, but you can assume that the wavefront sensor is making a reasonable measurement of the wavefronts without too much inaccuracy, then you can use what I call the naive estimator. And I'll show you more of that in a second. But we also assume that we have optical models for the way light propagates in the wavefront sensor and coronagraph optical systems. And of course, I'm going to want to know the noise statistics, basically photon counting and readout noise for the wavefront sensor and the coronagraph. So the input observations to the regression model are the millisecond frame rate science camera images, as well as the millisecond frame rate data from the wavefront sensor. So the outputs of the regression model, you get an estimate of the aberration coefficients, or sometimes, and depending what you're doing, that might be all you're going after. But you can also augment it to make an estimate of the image of the circumstellar material, so planets and disks. So So after I proposed that idea, a student in Arizona, Alex Rodak, and his advisor, Jared Mail, said, well, you know, if Rich has this scheme for measuring the aberrations that cause the speckles, why don't we try a control system with a 1 minute or so update rate that actually tries to remove, that compensates for these aberrations that are creating the speckles so that we don't even have these speckles to begin with. And so they proposed this flow chart here where you take the science camera and wavefront sensor data streams, and then you feed it to a regression and compensation set of algorithms, and then that feeds back into a deformable mirror to remove the speckles. So now that's when I started collaborating with the MegaOx team in Arizona, and we decided we would do a comprehensive set of simulations that would really validate this framework for real-time aberration correction. So what we've been doing lately is building up a set of simulations, and we have the, I'll show you what they are in a second. So in these simulations, we're starting with turbulent. We start with random phase screens that represent the effect of the atmosphere on the beam, and then we have a self-consistent simulation of an adaptive optics loop, and then the beam that's corrected by the adaptive optics loop goes to a chronograph, and when we simulated the noise of an EAPD operating at kilohertz frame rate. So anyway, you can get into the von Karman. So this is a turbulent wavefront. The von Karman spectrum is a lot like the Kolmogorov spectrum, and you can use that to generate random phase screens. So we did. And so this is this is a movie that shows our adaptive optic simulation. So on the upper left, we see the AO residual, and then the pyramid wavefront sensor makes 4 images of the pupil, and here they are. And you analyze these images to calculate what the correction should be, and then when you bring the light through the chronograph and make an image in the science camera, you get what's below. So this is a millisecond. This is what the chronographs and AO system provide at the millisecond time scale. So we wanted to simulate, well, what could we do with just 5 minutes of simulated sky time? And the idea is we would start with a large aberration, 30 degrees RMS, and in that 1 minute, which gives us 50K exposures, can we calculate a correction to that aberration that is useful? So, in your first minute, you get rid of the big aberrations, and then in phase 2, in which we simulate a 4-minute observation, the leftover aberration after the first phase was much smaller, and so the idea was that we would do a more sensitive 4-minute observation to re-estimate this much smaller aberration, as well as make a joint estimate of the image of the stuff around the star. So if I do a 1 minute average of the science camera data for that first minute of the observation, what we see we see this very distorted Airy pattern with the stuff coming off of it. That is a result of those 30-degree RMS aberrations propagating through the chronograph and then taking the turbulent time average. Now, on the right, this is a single millisecond exposure with all the noise in it from the chronograph. So Now, when we estimated those aberration coefficients, the aberration consisted of 36 Zernike modes. You can kind of think of Zernike polynomials like Legendre polynomials, if you're not familiar with the Zernike modes. But it's a 2D it's a 2D polynomial defined on the circle. And so our aberration of 30 degrees RMS was consisted of these 36 Zernike modes, and the true coefficient values for the aberration we made up are given by the black dots, and then the ones we estimated are given by the orange or yellow symbols, and we did that for both the magnitude 6 and magnitude 8 stars, and we made a pretty good estimate. And this was with the naive estimate, so we didn't assume anything about the statistics of the AO residuals, but that made us susceptible to the errors in the wavefront sensor measurement. So, but nevertheless, we made a pretty good estimate. So anyway, a little more illustration of what we did. So up in the upper left, you basically see an aberration map. When you add all those Zernike modes together, that's the phase and radians that you get. And then that's that same science camera image you saw. But then after we estimated, we simulated a deformable mirror to perform a compensation. And so the residual aberration is shown here in the upper right. And you can see it's much smaller. In fact, it's a 96% reduction in the RMS. And then you see the chronograph image on the lower right is getting pretty close to the perfect Array pattern. And we did that with only 1 minute of simulated data. So now now in the phase 2, this is the 4-minute observation with estimating a much smaller set of aberration coefficients. And for that, we have the bias corrected estimator, which takes into account, which leverages the knowledge of the statistics of the AO residual. And we also did the naive, but it wasn't nearly as accurate as the bias corrected. And so the naive was, you could see the purple estimates are the ones to look at here, and they're extremely close to the black dots. So we really nailed that down and estimated that aberration very well. But simultaneously, we estimated an image of material that we put around next to the star in the simulation. So what we did here on this left, the far left is the science camera image for phase 2, and that has the image of the circumstellar material in it. And so you can kind of see this part of the image just to the right of the star, but before this bright mark. That's a little brighter than it is on the other side. That's because this image here is placed in there before doing the turbulent time averaging. And so the image that we put in is on a 13/8 sky grid, and the sky grid points are spaced by 1 lambda over d, so 1 resolution element. And so the point is so here is our estimate of that image, and it's very close to the image. And so it has the same morphological structures. So we don't have the problem that we saw with ADI of a distortion of the structure coming out of the way we process the image. So it's a true image without the artifacts associated with the ADI. So now, because it's a regression model that allows us to, part of the output of the regression model is an error covariance matrix. So we had a little bit over 100 image points on that grid. So we had to estimate 13/8 quantities. So I think that's 104. So there are 104 image points, and those were simultaneously estimated with the with the 36 Zernike modes. And so we get a joint error covariance matrix to characterize the errors. Now I scaled this to have, so you can see the error covariance matrix. I had to scale it so it'd be easy to see. So I scaled it so that 1 is on the diagonal, and that makes it into a correlation coefficient matrix for those of you who care. But so the point is we get a self-consistent set of error covariances. Now, it turns out that the image of our estimate of the image is extremely close to what you would get if you had a perfect PSF subtraction. So if you knew exactly what the speckles were and you did an image, you would get something, you get what's over here, which is very close in error to what we estimated without that. So in other words, our image estimation method for this simulated case was extremely close to what you could get in a perfect world with non-millisecond imaging. But again, that takes perfect knowledge of what the star image is and subtracting that off. So, all right, so what are the next steps? So everything I showed you is just simulation, and then, of course, it doesn't mean anything if you can't do it in real life. So what I told you is that the regression models depend on having models of the optical systems, and so our plan is to use state-of-the-art optical modeling provided by the LightTrans software. And just this is from the LightTrans website. And so LightTrans implements a self-consistent method called field tracing. And that is a self-consistent that brings ray tracing and diffraction calculations together in a single unified self-consistent framework. And so they show that off with this example here. This is a diffractive lens system. So what's a diffractive lens system? Well, you take a kind of a standard kind of lens, but then you put some etching on it to give the surfaces some diffractive power. And so then you've got a device that, yes, you need the ray tracing to deal with with getting in and out of glass, but then you also have, the grooves on the surface mean you have to deal with the diffraction too. And so that takes you to the need for field tracing. So the whole point is we're not planning on leaving much to chance in the optical modeling. We're using the state-of-the-art capability that's available. Next, we want to use the modeling to do a tolerance of surface and alignment errors in the optical systems. And then after that, we want to demonstrate the aberration correction in the lab. And then after that, try it on sky and try to show some imaging and aberration correction. And I'd like to acknowledge my funders at the NSF and the Heising-Simmons Foundation, and my collaborators with MKids, MegaOx, and SkexAO. And I'm ready for your questions.
Yeah, or start here. Any questions?
Another star with an isoplanar patch of the very large instrument that just avoid using the same source.
I think he's asking about dithering, which I understand has to do with subpixel motions to sort of remove some of the pixelation from the imaging. Is that right? I think dithering can be useful. I think it's kind of a side issue, so I'm not sure why you, I mean, if you're asking about the off points and the effect on the chronograph of the off points, is that what you're asking about? Okay, let me handle that. So the chronographs are potentially pretty sensitive to off pointing, especially in space. And so I'd be pretty surprised if dithering was part of the plan. And then you asked, and what was your second question? I'm sorry. Oh, looking at other stars. So so it's often hard when you have an adaptive optic system. Unless it's a binary star, it's hard to find a star that's within the correction radius. There are schemes where people look at stars that they know don't have anything around them and try to get the speckles that way. And that's another form of differential imaging, which still has its own problems.
What bandwidth and what contrast rate you expect to get? Question. Can you repeat the question?
Oh, bandwidth and contrast. So the space-based, I think they're really shooting for 10 to the -8 contrast and maybe 10% bandwidth from the visible to the near IR. On the ground, the bandwidth I haven't explored very much. I'm really hoping within, it's really important to get close to the star because a lot of the stars are really far away. So the closer you can approach the lambda over D, the more targets you'll have in terms of where you can image effectively.
Are your simulations all monochromatic?
Yeah, they're all monochromatic at this time. When you get into polychromatic, you have to deal with the fact that your aberrations can have some wavelength dependence, and there may be some chromaticity in the atmospheric wavefront. Within, let's say, 3 lambda over D, I'm hoping, to eventually approach a 10 to the -5, 10 to the -6 contrast ratio. And I hope that, let's say a 5 to 10% bandwidth doesn't really stretch the models too much, but that the chromatic issues need more study.
That's from the ground, I see.
Yeah, that's for the ground.
First, why aren't you using laser guide stars? And second, why do you need to build a deformable mirror? Why can't you just do all the corrections in software?
Well, a deformable mirror allows you to actively cancel the aberrations so the speckles aren't there. In software, you can do regression and try to account for them.
Right.
But if you can just get rid of them in the first place,
But isn't a deformable mirror much more expensive than building the software system?
well, I don't know, a 30-meter mirror is pretty expensive.
I don't know how much the extra cost is.
No, a deformable mirror isn't that much money. And if you want to actually remove it, well, you had another question?
Well, yeah, you didn't mention laser guide stars.
Oh, laser guide stars. Well, so you definitely need natural guide stars to do this because laser guide stars have certain low order aberrations and so that they're not as good as, because the beam that a laser guide star starts in the sodium layer of the atmosphere and cones out from there, whereas the beam from the star is just all parallel and is the same shape as your telescope. That said, I am advocating for using laser and natural guide stars because I think you could do some kind of initial correction with a laser guide star and then save the stellar photons for finer corrections. If you want, I can talk more about that. Can you take off your mask and speak? I don't understand what you're saying.
What is the more important part of the selected wavelengths? Which infrared band that is important now?
Well, I think that can depend on the star. Where's the star brightest? Oh, which wavelengths do you observe at? It depends. I mean, it depends on where the star is bright. Depending on what your planetary target is, are you looking for thermal light, or are you looking for reflected light? So it really depends. I mean, there's use for all of the wavelengths, but that's kind of a case-by-case thing. Oh, okay.
So I know this is primarily the work that you're doing. Very good work is focused mostly towards ground-based observations. But I'm curious how this these methods that you developed compare to something like the proposed star shade.
Well, probably not the star shade so much, but the other ones. I have posted a paper on the preprint archive that almost nobody's read about when you dig the dark hole. The way they do it now is they use a deformable mirror to modulate the intensity in a pixel of the dark hole, and they take the intensity measurements to do a regression on the electric field in that pixel of the dark hole. And then once they know what that electric field is, they can figure out what deformable mirror configuration will cancel that electric field to make the destructive interference better. But my approach was, instead of doing that, why not solve for the aberration that's making the dark hole not dark and regress on that aberration and do it that way. So I think there's some transference of the methods in that way. It hasn't garnered much interest yet, but there's more time.
But if people want to continue, there are some slots open for them during the speaking session. So.
All right. Well, thank you, everybody.
My question is,